Hi everyone, I'm Xu Jiayun from Singapore Management University. My presentation is about the paper Differential Training, a generic framework to reduce label noises for Android malware detection. In learning-based Android malware detection approaches, the labeled training set is usually very important since classifier will learn from these labeled samples on the features of benign and malware and use the learning knowledge to identify the unknown samples and make the malware prediction. The current approach to label sample apps is not perfect due to a couple of reasons. First, the labels provided by the malware detection websites are not always reliable. For example, we randomly collect 50,000 of samples from VirusTotal and download their scanning report twice in 2016 and 2018. During these 2 years, we found about 10% of them, which is more than 5,000, have their scanning results changed, which means there will be mistake in this scanning report. The label lines may distort the Android malware detection in two main aspects. First, the label noise will worsen the performance of classification model trained by them. The second, if the testing set is questionable, which means you cannot judge the real performance of these approaches. And this situation is even worse due to the ever-growing size of datasets in nowadays machine learning-based Android malware detection approaches. It is also very highly challenging for even domain experts in malware detection to ensure the correctness of data labels because in nowadays the techniques for composing malware are highly complicated. We believe that this is one of the reasons there is no universal benchmark dataset that has been built for Android malware detection so far. In this case, we propose differential training. Differential training is a general framework that is compatible with different Android malware detection approaches, and it can help reducing the label noise in the dataset when differential training works with any specific Android malware detection approach. Differential training relies on the heuristic, that is, in a deep learning-based Android malware detection approach, the loss value of correctly labeled samples are different from those of wrongly labeled samples. Here is the observation that enlightens us about the heuristic. In this figure, the x-axis is about training epochs, and the y-axis is about the average of the current loss value divided by the final loss value. In the figure, the red line means all the currently labeled samples, and the red line is the average of them. And the green line is all the wrongly labeled samples, which are the label noise. And we can see that the green line here is different from those of the red line, which means there exists differences between the loss values in correctly labeled samples and the label noise. Here is the overview of differential training framework. The differential training is composed of three phases. The first phase is pre-processing. The second phase is training of the WS model and DS model. In this phase, the label noises are reduced gradually in multiple iterations. And the third phase is malware detection with revised labels. In phase 1, the first step is generating feature vectors for the dataset samples. And the second step is assigning these feature vectors with corresponding labels. After this phase, we got a set of feature vectors that is produced by the approach. And all these feature vectors are mapping with their corresponding labels provided in the dataset. Phase 2 in differential training is named the training of WSDS model. Note that the phase 2 contains multiple iterations. In each iteration, 2 different models will be built and there are 4 different steps. And label noise are gradually reduced in each iteration. The first step in phase 2 is dataset downsampling. In this step, differential training randomly chooses some samples from the whole noisy dataset and create a smaller downsample dataset. We denote this one as the whole set, and this one as the downsample set, which is short for DS. All of these sets will be used together in the following steps for the loss value collection. And here's the explanation of why we use 2 models instead of 1. In the toy experiment, we first downsample the whole set into a smaller downsample set named DS. Then we use both of these sets to separate models. One is named WS model and second is DS model. They are both deep learning models. And for sample A in the downsample set, we collect its loss value in all the training epochs from WS model and shown here, and collect all its loss values in all the epochs during the training of DS model and shown here. For the loss sequences in sample A, we denote that the first loss sequence of sample A in the DS model is alpha D, and the last loss value of sample A in DS model training is omega D. Similarly, the first loss value in the loss sequence of sample A in WS model is denoted as alpha W, and the last is denoted as the omega W. Given the selected values, we built 3 different toy loss feature sets based on these values to try to explain why using 2 models will be better than 1. The first value is alpha D divided by omega D, and the second value is alpha W divided by omega W, and the third value is arctangent of this value divided by this value. And then we apply these 3 feature sets on a whole set containing 50,000 apps, and downsample set containing 3,000 apps. Well, in the whole set, there are 10% of them we manually flip them to generate noise. And we use stack, which is an Android Malware Detection approach published in TDSC 2020. The figure shows that the distribution of correctly labeled samples, which are in form of red column, and the distribution of noisily labeled samples, which are labeled noise, that are shown in the blue column, and how they are different when we use 3 different kind of feature sets. One is from 2 models simultaneously, and the other 2 is only from 1 model. The blue line is the feed curve of the distribution of wrongly labeled samples, while the red curve is the feed curve of distribution of correctly labeled samples. From this, we can see that collecting loss values from 2 models simultaneously can help maximize the difference between correct samples and label noises. With the above toy experiments, it is shown that why we use 2 models instead of 1, because using 2 models can have a better performance and help us to distinguish label noise from correct ones. So this is why we have 2 models here. After the 2 set, the whole set and downsample set are generated, we then use each of them to train a single model. Since we have 2 datasets, we have 2 models. One is named WS model. The second is named the DS model. These 2 detection models are of the same network architecture, and they are trained by the WSEF set separately. After these 2 models are trained, we start to collect the loss in them. Different from what was shown in the toy experiment. In differential training, we use all the loss values instead of the first and the last value. In the WS model, all the loss sequence of a sample X is denoted as L1 until Ln, and the same sample X in the DS model, all of its loss values during the training process of DS model is denoted as L1 prime until Ln prime. Then we concentrate these 2 sequences together to generate our loss vectors for outlier detection. Since these 2 models are trained separately, they will have different number of epochs. There are no relation between the N and M here. In the last step 4, outlier detection. Based on our heuristic, the loss values of correctly labeled samples and wrongly labeled samples are different. So we put all of these loss vectors together and using outlier detection algorithm to find out which one is different from others. The outliers here are thus regarded as label noise, and we manually flip their labels as the correction on the noise. After all the iterations in phase 2, we believe that the noises are reduced as much as possible, and then we apply the given Android Malware Detection approach on the process labels to see its performance. And here is the evaluation part of differential training. We evaluate differential training with 3 different Android Malware Detection approaches, which are stack published in the TDSC 2020 and Drebin published in the NDSS 2014, and Deeprefiner. The table shows the overview of these three datasets. From this table, we can see that compared with the stack, the Drebin has a very imbalanced dataset. It has much more benign than malware here. So using the three approaches, we can tell that how differential training works in different cases. Since in the beginning we find that the labeled dataset may contain noises, we further download their latest scanning results from VirusTotal in July 2019. So when we download the latest scanning result, we compare this result from their original labels in the dataset, and all the samples with different labels will be removed, which means all the remaining ones have only contained the samples whose labels are stable in the past several years, and we regard them as their labels can be trusted. Then we manually flip the labels of a certain ratio of samples to generate a dataset with a given noise ratio for evaluation. This is the evaluation result of differential training when it works with stack and its dataset. The table shows that in each iteration, how many samples are detected noises, and whether the detected samples are in fact labeled noise or they are false positive. And we can see that with all these more than 50 iterations, the accuracy of the label are increased from 90% to more than 98%. And there are always more true positive than false positive during the whole process. And the table shows the detection result of differential training on stack. We can see that in the beginning there are 10% of noises, and after that we detect more than 5,000 of true positive noise, and we have only 300 correct labels that are wrongly detected as noises. And after all the processing, we can see that the noise ratio is reduced from about 10%, 1.26%, which means differential training can reduce the noise ratio by 80%. And here is the F-score of stack working on the correctly labeled dataset, working on the label set with 10% of noise, and working on the dataset that is processed by differential training. And from this F-score performance, we can see that with differential training, we can increase the performance of stack by 8% in measurement of F-score, and is very close to stack when it is evaluated on the ground truth dataset. In this case, it is shown that differential training can help reduce the label noise in the dataset and increase the performance to make it more close to its actual performance. And this is different training evaluated with the other two Android detection projects. One is Drebin and the second Deeprefiner. We can also see that in the Drebin with highly imbalanced dataset, different training can still reduce more than 80% of noises and increase the performance of Drebin by a lot. And here is the performance of Deeprefiner. It is also shown that when the F-score when its original performance on the ground truth dataset is not as high as the other two, we can still detect and reduce the majority of noises in this dataset and increase the performance to make it more close to its real performance on the ground truth dataset. Here is the evaluation result of differential training with three Android malware detection approaches when the noise ratio in the dataset of different values other than the default 10%. In all these experiments, differential training can detect a majority of the label noises, and it can not only work with different Android malware detection approaches, but also be effective with different noise ratios. Thus, it is demonstrated that differential training is in fact a generic framework in reducing the label noise in Android malware detection research. That's all about it. Thank you for listening.